Hello and welcome back. Today we are going to continue our discussion on using the triple integral to find volume. So we want to find the volume of between the solid given by our cone here and the circle on the xy plane. Now we know the circle is on the xy plane because there is no z value, so this is definitely on the xy plane here. That's again because z is 0. And we want to find the volume between the two. So if I kind of graph it out in third dimension here, in 3 dimensions, there's my x, there's my y, there's my z, and I can go right here because we are dealing with 3 dimensions here. This is our cone. It's a parabola, elliptical cone, so it's going to look something like this, and it crosses here at 7, and we have the circle, which has a radius of 2. 2, 2, negative 2, negative 2. And we want to find the volume that this circle, if we were to project this circle up to the surface, we want to find this resulting volume. All right, so let's go ahead and get started. Now we're going to use a triple integral. So for a triple integral, to get the volume, dv, remember it's going to be dz, dy, dx. You can change these around. We're going to talk about those a little bit later on today, but you are able to change these around. But the first thing we want to find is our change in height. That's our change in height. And this one gives us, and this one deals with how the base is changing. And of course the base here is going to be our circle. So let's go ahead and set up our limits. To get our limits here, to get the change in height, delta z, well, delta z starts at the bottom. Well, that's going to be our circle. So what's our circle, or in this case, z is going to be 0 because we're just going to be on the circle right here. So my smallest my z value will be is 0. That's on the plane right here, down at the bottom. Z is 0. And if we draw anywhere from here up to the surface, that's going to give our maximum z, which in this case is going to be this parabolic cone, 7 plus x squared plus y squared. Now we have to talk about the base. Well, the base is the circle down here at the bottom, and I'm going to use a vertical rectangle. In other words, I'm going to be able to change in y's right here. And if I look over here, back over here, since I'm doing vertical, this deals with my change in my y value. So this right here will be my minimum y, and over here would be my maximum y. Well, to get the minimum y, this is just our line, our circle right over here, and I can solve for that. That would be y equals negative square root of 4 minus x squared to positive square root of 4 minus x squared. So that's my change in my y's. Negative square root of 4 minus x squared to positive square root of 4 minus x squared. And to get my change in x's, well, remember this is going to go horizontally, even though it looks like it's vertically. Remember my xy plane looks like this in 3 dimensions. We're going to go from negative. This rectangle is going to go from negative 2 all the way to positive 2. Oops, I should use same color. Negative 2 all the way to positive 2. So our volume as a triple integral, remember, spread these out, makes it look nicer. dz, dy, dx would be from the change in z, that's the first one, because remember when we integrate, we always start with the inside, 0 to 7 plus x squared plus y squared, negative square root of 4 minus x squared to positive square root of 4 minus x squared, and from negative 2 to 2. You can, of course, use symmetry because this is a very symmetric figure. If you go from 0 to 2, you can multiply this by 2. Heck, you can even let the y's go from 0 to here and 0 to here, and you can multiply by 4. And that would work as well. So remember, this part right here, the dy dx, this right here represents the part projected to the surface. This is the projection of that circle to the surface itself. The dz, well, this is my change in height. Right there. Now, if we want to have some fun, we can actually convert this to polar. And we're going to talk about this tomorrow or the next day. If I convert this to polar, my base, see right here, this is x squared plus y squared equals 4. I can actually use my formula, x squared plus y squared equals r squared. And I can use that to kind of rewrite over here. So as a polar function, it would look exactly the same. We're still going to use dz. But remember, in polar, remember this dA was dy dx in rectangular. In polar, it was r dr d theta. So it's going to be dx, I'm sorry, not dx, but dz r dr d theta. So the change in z is still going to be the same. It's going to be from 0 all the way to 7 plus x squared plus y squared. But remember, in polar, what is x squared plus y squared equal to? R squared. So this is just 7 plus r squared. Now, if we think of the circular base right here, if we think about the circle, has a radius of 2, ready? The change in radius goes from 0 all the way out to 2. So that's just going to go from 0 to 2. What's theta going to do? Well, theta, remember, it's going to go all the way around the circle, 0 to 2 pi. And which one looks a little bit easier to solve? Now, the only thing different I would do, though, is I would really put the r here, so we should really write r dz dr d theta. It's how we should write the inside there. All right, going to video number 2, we're going to take a look at some examples about how we can change the order of the dz, dy, dx, and how that affects our integral itself. See you then. Bye-bye.